good morning. So what Boyd and I will talk about, well, we call it problem-led software design. I'm looking a bit more from the Erlang point of view, the original Erlang point of view, and Boyd will be looking from some of the more fun projects he's been doing, which I'm really waiting to hear about. Anyway, yes. So let's see if we get the right mouse. There we go. So what was the Erlang problem, right? We were trying to solve something, but what was the actual problem we were trying to solve? And the general one that the lab was looking at was how we could improve the programming of telecom type applications. So the AXE switch, what Ericsson had, was a very successful switch, but it was quite complex to maintain and develop. So we started looking at the problem, how could we improve that? That's a very general problem. It sort of says everything but says nothing. And we needed to while we were looking at our ways of solution, we had to put a lot of work into working out what was the actual problem. And these, I think you've seen before, these are some results that came from all these thoughts about it. They came from a thesis Bjorn Decker, who was the boss of the lab, wrote about these things that were important for it, like the concurrency, the timing constraints, etc., the fault tolerance, all these things. We sort of, as our thoughts about what the original problem was, this one was, we found that these were things that had to be taken into account. So now we're sort of getting the problem, defining the problem, right? Unfortunately, there's still pretty general ideas. I mean, handling very large numbers of concurrent activities, what does that actually mean? And things like this, and timing and stuff like this. So we had a original system we were experimenting with. It was actually written in Prolog, but that's in one sense irrelevant here. And then we did a lot of experiments trying to work out how we thought you could write the application and how you could solve these things, right? So we ended up with, well, again, we found afterwards, this is not just telecoms. This 5 years later, we found people were doing really weird stuff using our system, which we'd never thought of originally before. But yeah, so what happened is, so internally, there were lots of threads going on, different thoughts going on how to solve this problem. I can say now we're quite happy stealing ideas from other people. A lot of these things we took from other things. I mean, some of the things operating system like, there was another language called Pascal at Ericsson, which also had Pascal with concurrency. So we'll look at these. But a major problem was understanding what the actual problem was, right? So we could say making lots of calls, but what does that mean? And so that was trying to understand that section, as well as at the same time designing a language and architecture which could be used for building these types of systems. So we're not out to write a telephone switch, we're out to do an architecture or a system to build language for doing these types of systems. And there was a lot of looping here through it. So we were thinking and came up with ideas. We'd do experiments to test these ideas. We'd then go back and see, is this the problem? Are we attacking something which is the problem or not? And so there was an enormous amount of looping going around at this, thinking, yeah, we could do this would be one way of solving the problem. Could we think of a way of writing a language or system for solving that? Then we could say, does this solve the problem? Does this provide concurrency in the right way? Does it provide error handling? What does error handling mean, right? What does a fault tolerance system mean? Does it mean nothing can go wrong? Or does it mean some things could go wrong, but the system must survive afterwards? Just working out these things. By the way, that was the second one where we ended up with the right way. So we were working in this loop, testing all the time our ideas, writing systems, trying to write a telecom system, a small switch, controlling a switch, using these ideas and seeing if it worked. But at the same time, so the original three of us was Joe Armstrong, Mike Williams, and myself. Joe and I came from the outside world and knew very little about telecommunications at the start. Mike had worked, I think, 10 years, something like this, before for Ericsson, so he had a very good idea of what was going on internally in the system and what it actually meant. I can also say all our ideas of solving this problem, they were different from the way they've been solved in the AXE system. So we're looking at different type of solutions to try and solve these problems. But then we were very lucky. So we came up with some things we thought would be good for this, but you have the real world outside, which it has its own view of what the problem is. And we were very lucky to work together with another project in Ericsson called ACS Thunder, who were looking at building an architecture or designing an architecture for smaller systems. And we worked together so they would test it. They were very interested. They tested our ideas and came back with a lot of good feedback. Well, a lot of feedback. Some of it was positive and some of it was negative. But they had a much better, well, they of course knew what the problem was and what was important in the problem. They could give feedback on that. What are our ideas for concurrency? Were they good ideas for concurrency? Were our ideas for fault tolerance and handling? Were they right and things like this? And they would come back with feedback, and that means we'd have to start rethinking and come up with new ideas, improve the ideas, and give them back to them, and they would come back and say yes or no and things like this for it. They ended up being the first users, right, actually using Erlang in a product. So these diagrams are pretty easy, simple, but where we ended up was something looking like this, right? So we had our internal development. This was in the lab where we were thinking and doing experiments. We were then passing them over and discussing these with the real world, i.e. the ACS Thunder group here, who would then look at these ideas and see how they could use them, if they were suitable or not, and then come back with feedback for us. And we'd be going through this double loop all the time for it. And eventually we arrived at something which worked, which was suitable. It worked. It could do what it was supposed to do. They could use it to build real systems. I mean, they did a prototype of what they were thinking about. It was something like 15,000 lines of code, controlling a real switch, doing the important bits they were interested in. So that we could come back with our ideas here. And I can say along the way that, I mean, they said some of our ideas were good and some were bad. We tried to make solutions, which were usually wrong, but anyway. So this whole loop, our solution was evolving at the same time we were our idea of what the problem was evolving at the same time, working out what the real problem was, and trying to make something. A system on which you could build solutions to this type of problem, not just one problem for it. And so where do we all end up with this from our point of view? I just want to go, I'm not going to go through the top things, but we arrived at the solution that there's a lot of concurrency going on here in the system, and the best way of doing this, we felt, was having processes. We call them processes. They'd be very simple processes, but having lots of independent processes. That was the best way of doing it. This was completely different from what the AXE system did before. But also meant processes be coming and going all the time. So creation, context switching, communication had to be fast, because that's what it's all about. You don't have one process doing lots of things. You have lots of small processes doing lots of things, communicating with each other. We ended up again that asynchronous communication was the right base, because that's what the problem required. And using asynchronous communication, you could build up any level of synchronous stuff on top of that, whichever layer you wanted. It's more difficult going the other way. If the base was a synchronous communication, putting asynchronous communication on top of that was much more difficult. Next to the process isolation, the error handling, that worked together for our way of doing fault tolerance. That we felt in most cases, if something went wrong, it was suitable to crash that process and let the system handle that, detect that the process had crashed and do the right thing. So therefore, you need process isolation, because if a process crashes, it can't ruin things for other processes. But you need the error handling mechanism there so you can detect when processes have crashed and handle those. This was the linking of the error handling before. The continuous evolution, that was that it was a requirement that the system had to be able to be upgraded while it was running, upgraded code and things like this as well. So we need to work out how to do code handling at runtime. And then, of course, there was a soft real-timeness. The system was not allowed to block. When something happened, it had to do something within a certain time, and things took a certain amount of time. So we had to make sure that the system was non-blocking. That meant that's one of the nice things about the processes, because when I'm writing my process, I don't have to worry about blocking, because there's an underlying system, a schedule underneath, which will make sure I don't block the system. We called it soft real-time. real-time people say this is not real-time, because sometimes we had to run over, it wasn't too bad. For our type of problem, this was perfect. And there's some other things as well too we arrived at, again, while trying to work out what the problem was, right? And we wanted a high-level language. So, well, comparative to those days, we're talking late 80s, early 90s now, and we wanted a high-level language for it. And we also felt that the language in the system itself should be simple. You don't want complexities at the lower level, because that makes things much more difficult higher up. So we put a lot of work into making the basic primitives, basic concepts simple. And in simple in a sense, there should be a small number of them. If you get them right, you can build everything on top of that. So for example, if you look at the concurrency model, there are 4 or 5 basic principles, depending on how you want to count them, on top of which everything else is built. And the same thing with error handling mechanisms. And we also want a language that was simple to understand and program. We felt the language is simple. Whether it's simple to understand it, that's another problem. Again, we also found out the hard way that we should provide tools for building the systems, not doing solutions. We a number of times tried to provide solutions which we thought the ACS Standard team could use, because that would make things much simpler for them. But we basically usually got it wrong. So a number of times we came back, we'd misunderstood what the problem was, so trying to provide a solution to the problem was something, said, yeah, this is fantastic, but we can't use it. And that, seeing that complicated the system, we removed it. And again, the second point here, this should be simple, that grew, and it actually takes quite a bit of effort to do that. Dijkstra has a quote, I can't remember exactly now, where he's saying that's difficult to do, it's hard, it takes effort to do it, it's hard to understand it, and also it doesn't sell as well either, to be honest. Yeah. So this is the type of things we were doing in our system and working. And the whole thing was that our view of the problem, what the actual problem was, evolved at the same time we were trying to provide solutions for it. And we got feedback from the ACS standard saying, yeah, this is not a problem, or this is a problem, and what should be done like this for it. So the whole thing evolved at the same time. And that's sort of why, more or less, why we ended up where we are, where we were. I think that's pretty much my bit here. Yes. So now I will stop sharing and hand over to Boyd, who's looked at other types of problems, different problem domains also. We're doing things for it. So yes, I'll stop sharing here now.
All right. Well, thank you, Robert. And it's really cool, and it's always fun to see. And I'm a huge fan of the work that you've done.
Okay, thank you. Thank you very much.
Right. There was a point in time it was about early 2015, mid 2015. I'd left Microsoft, and shipping Xbox One was frankly really draining. I was kind of burned out. I needed some time off. When I started really searching for what I was going to do next, one of the first things I did was I kind of knew the properties of the engine that I wanted, and I wanted to understand the world outside of Microsoft. So I kind of went language to language and virtual machine to virtual machine, and I wrote enough code in each one that I could kind of wrap my head around it and understand it. And I rejected pretty much everything. And then I got to the Beam, and I started to wrap my head around the properties of the Beam, and I fell in love. And it was one of those things where I could tell that you had been focusing on the problems, right? And when I found, the async nature of the communication, the process isolation, then I wrapped my head around OTP, and it's like, okay, this is a beautiful thing. Got to say, the syntax wasn't my cup of tea.
You are not alone there, I'm afraid.
Right. And then I found Elixir, and it's like, okay, I'm done. I know what's going to be the center of whatever it is I'm doing next. So I'm going to share my screen now, and let's talk about part 2 of problem-led software design. Okay, can you see it okay?
Yeah, fine.
Okay. Okay, so problem-led software design. I actually started to get formal about thinking about this around 2004. So when I was on the Xbox team, which I started on in about the year 2000 and ended when I left the company, So the first 4 years I was running engineering for Xbox Live, and then 5 years on a project called XNA, and then 5 years on the Xbox One console running the OS team. At the beginning of XNA, which I'll talk about in a bit, I actually started to get really formal about, well, how do we come up with the software that we're building? And how do you know you're building the right thing? Engineers have a tendency to come up with a really cool idea. That's the thing. That's what I want to go build. And you really got to pause and stop and ask a few basic questions. So for me, the 3 basic rules around problem-led software design is, number 1, got to build for the future. If you're picking problems that you have right now, then you're going to spend however long you need to spend building something. You'll be done with it, and it won't be relevant anymore because the problems will have changed. So you have to sit and look ahead and try to predict what the problems are going to be at the time that you're done with what you're building, instead of what the problems are at the time you start. 2, and also equally important, is that the problems you pick have to lead the way to the solutions and not the other way around. Do not decide what you want to go build and then start looking for problems it solves. You've got to focus on, this is the set of problems that are interesting. And from that, you'll intuit and figure out what the solutions are supposed to be. And then thirdly, again, just as important, is you have to know what problems you're not solving. And if you can, take the time to articulate them. So this kind of becomes a process of problem discovery. And kind of loosely, I think these kinds of problems fall into 2 categories. There's problems of purpose. A problem of purpose is, well, what business problem am I trying to solve? What's the actual customer problem that they're having, and why they need the thing, why they need a solution? And then there's problems of platform. The customer might not necessarily vocalize these, because this is sort of what Robert and I have both done in our careers, is we've built platforms, right? We've built packages of software that other people build their software on top of. And the problem with building a platform is that you don't know what you're supposed to build until there's an app. But you can't build the app until there's a platform.
Yes, yes.
Right? So what I find I end up doing is you do a bunch of research, you make your best informed guess, and you have to take a stab at one of them. Usually the platform first. You build a bunch of stuff, and then you start building an app, and you realize, oh, I screwed that up. I didn't understand this problem. And then you kind of circle around, just like Robert was saying. You end up in this circle. And I tend to call it looping, where I start with a great big outer loop, and then it gets tighter, and it gets tighter, and sometimes it swings back out during a refactor, and eventually it starts getting smaller and smaller, and you get to the center. So that's when you're being your own customer. So I want to give a couple examples of times when I've been kind of formal and kind of went out of my way to try and understand the problems. The first one was in XNA. So XNA is a product that doesn't exist anymore, but it was something that was really important, and I'm still super proud of it. And XNA stands for XNA is not acronymed. Okay, so the year is 2004. We're working on what would become Xbox 360, but it has not been announced yet. Okay, so I'm setting the stage. All we know is that when you move to higher definition gaming, the cost of building gaming is going through the roof. Right? So basically what I'm describing is, this is the problems that we started assuming. This is the problems we went in with. Cost of building a game is going through the roof. People are spending gobloads of money making games. There's really no industry pipeline standards, meaning that game teams would build their tool chain, they'd build their engine, and then chuck it. They would just throw it away for the next game. When I talk about poor art control, I love Git, and I love using Git, and I love the modern source control. And we all kind of know you're not really supposed to chuck binaries in it. But in a game, you can easily end up with 20 terabytes of binaries in your history source control. In fact, it's like 99% binary. So the tools don't really work, and that wipes out your network and all kinds of issues. So that's what we went in with. We were pretty sure these were the important problems, but I actually purposefully got in a plane and flew and talked to all kinds of game developers to confirm that this is really the problems that they faced. And what I heard, they all said, yeah, these are the problems that they have, but instead, This is what they wanted to talk about. And I've switched the X and A logo because this is the stuff that ended up becoming really important. The old logo was like when it was still incubating, and this is the one that actually shipped. What I heard was that developers were suffering some kind of SQL burnout, right? I'm on version 5 of the same game. Everything's a giant game. There's no ability to make little games. There's no indie market. There's no indie game scene. And there was a lot of angst amongst the developers that it was all just these big blockbusters, and there really wasn't any kind of need, or there wasn't any kind of a world where you could have small games. So what we shipped was, all right, well, let's throw away our first ideas because the actual problems that we're hearing are different. So we opened up the Xbox. You could download a set of tools, put it on your PC. I think it was $100, and you could write any game you wanted and shove it over. And then we built a game store. It built a big C# game framework. Why I think it isn't still around is we didn't nail all the problems right. Or rather, maybe we were a little ahead of our time. We shipped all this stuff just like a year before the whole smartphone thing took off. And that was really a better place for the indie games market. Indie games on a game console had to compete with the AAAs, and it's just hard to get airtime and hard to understand what people want. But it still left its mark. When you use Unity, and if you use monogame, there's C# is the language of choice in those packages for a reason. So when you think about the problems you're going to solve, you end up having a bigger impact. This is my first really clear understanding of this. So we'll fast forward a good ways. The big thing I released so far since I left is Scenic. And let's see, I think I unveiled that at Elixir Conference 2018. But I went through the same process. I really sat and thought, well, what problems am I trying to solve with this? And let's get those and understand those before I start writing a lot of code. And this is a sampling of some of the problems. It's not a full list. But you know, when people are writing devices, and I was really thinking devices, I'm not thinking necessarily PCs, I'm not thinking websites, I'm thinking about things like a console, or things like a connected device or an IoT. I really don't like the name IoT, I prefer connected device. When people write the UIs, they tended to conflate the control logic with the UI logic, right? So that when a piece of UI would crash, you'd lose the whole thing. I remember driving my car. I had one of the early Tesla Model S's before we moved to New Zealand, and now we drive in the left, so I left the car behind. You know, every once in a while, like the mapping app or some app would crash in the main console, and it would take minutes for I had that part of the car back, right? So recovery time was slow. On phones, on Windows, on Macintoshes, the UI that you build has the look and feel of that platform. But that's not necessarily what you want when you're building a device. So I wanted a host OS independent kind of system. And then finally, if you're building a device, don't put a web server on it because you don't open ports. You just can't have open ports. Secondly, don't put a web browser on it because you're trying to make a small, inexpensive device, and what you're first thing you do is put down how many megabytes worth of web browser with the JavaScript engine, and you're pulling down stuff from where? So you have to think about security. So I wanted lightweight, small, I wanted good error handling, fast recovery, wanted to separate the concerns of business logic and UI logic and that sort of thing. So that's effectively what I built with Scenic. Scenic is heavily based on the OTP hierarchy. Every little control on a Scenic page is a process. When you press a button, it sends messages through the chain and across different processes to get the logic to actually happen. The UI is loosely coupled to your control logic, which is often a completely different part of your OTP tree. And this allows us to do things like when a piece of your UI were to crash, or when there's some kind of an error, that can reboot extremely quickly while the control stuff just continues running. The goal there was, when I say fast restarts of pieces of the UI, I wanted to be able to crash an entire scene, have it completely reconstitute and start growing again faster than the frame rate of the machine, which means that the user won't even see it blink. And I'm really pleased with the performance I got from the Beam on this. Then native graphics primitives, really, like I set out saying, the only dependencies I'm going to take are OpenGL and the Beam. absolutely nothing else. So it looks exactly the same, whether it's running on my Mac or in Debian or on Nerves or on anything. And the last bit with the forward-looking driver model, that's a set of problems I really didn't discuss before. And maybe I'll come back to that in a little bit when I get to the third piece. But now we're going to do a slight detour. We were talking about the looping that they went through when they did Erlang. And remember how he was talking about you get feedback from the customer, and then they would go and do a bunch of research, and they would go and come up with new things, and send it back out. In my theory, so I've always called this the Jello theory of development. And as I've learned in New Zealand, it's jelly. And I have no idea what it would be in Europe. So the Jello theory of development is when you're making a dessert, when you're making a Jello dessert, you add the sugar and the gelatin and the boiling water, and you stir it all up, and it's a nice hot liquid, and then you add the cold water. And as you're stirring, it's still completely liquid, and it's swirling around, and it's forming, and eventually it starts to cool, and it starts to set. You can still stir it, you can still move it, but it's starting to give some resistance. And then a little bit more work, a little bit more cooling, and it starts to set more. Eventually, it's pretty much in the shape it's going to be, and you can take it out of the mold and put it on the plate. So you tip it upside down, you put it on the mold, you lift the mold off, and it's going blah, 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 blah. It's all wibbly wobbly. And then that starts to die down. And eventually, you have what looks like your dessert. But if you tap it, it's still going to move a little bit. Software is never completely done. Right? And this is, it's an analogy to try to describe the exact same process when you're building platforms. You build the platform, you build the client, come back to the platform, you go back to the client, you spin around and around and around, and eventually it stops shaking, and you have, oh wow, I never finished that slide, hacking target, how efficient such a much. That was from a different one. Anyway, so the story is important, not the words. Okay, so let's go through, what am I working on now? So I left Microsoft, and I wanted to do something, a whole bunch of experience building big, fat, hot connected devices, which are called consoles, but are effectively like an IoT kind of thing. This led me to have a lot of opinions on what worked and what didn't work. So I did a lot of problem discovery up front, talked to a lot of customers. I flew to the UK. I actually did a tour of infrastructure providers in the UK, just asking them, how do you run your devices? How do you collect your data? Lots of modeling, lots of research, a lot of experiments. In fact, this is the phase when I went language and engine to engine, and that's how I found the Beam, was during this phase of the problem discovery. And in the space of connected devices, the set of problems that I identified were these four. There's actually more than the four, but these were the top ones on my list. Number one, what I heard from these people was they were worried about security. This was right after the NHS had gotten bricked by ransomware. This is as people were realizing these devices are going into really critical systems, factory control, infrastructure, all kinds of important stuff. They're worried about hacking. They're worried about security. They were worried about, how do I know that this device is going to stay in my control? Because remember that by definition, these devices are not in your control. They're not in the place where you are. They are off out in the world doing something. They were worried about robustness. Hey, software has errors. It's not perfect. So how do I have some kind of sense that this thing is going to be able to heal itself and it's going to keep working? They're worried about flexibility. Specifically, how much time and money do I have to spend to build something? Right? And every time I have to put together a custom system and get the right drivers in place, and I have to spend all that effort and worry, is there some way I can bring that down and make it more manageable? And then manageability is about remote, because again, these things are not where you are. In fact, they could be up in space. You don't know where they are. They're just not with you. So that's what I set out to do, to try and solve. Scenic, by the way, is actually the first piece of the solution here. That was addressing robustness with UI, and it was effectively an experiment on my part to help me move toward an eventual solution here. And it fits into a larger puzzle, which is, by the way, why Scenic isn't done yet. It's because I had to go and solve some other stuff before I can move ahead with it. So what I'm actually building, I've got a company here in New Zealand, calling it Crichton, and we're building an operating system, like pretty much from the ground up. And it's got several properties. First off, I'm full on in on the Beam. Beam is my first class citizen as far as application environments are concerned. Just like nerves. By the way, I love nerves. So as I'm talking about this, no confusion. Huge fan of nerves. Nerves and the Crichton OS kind of solve slightly different problems, and that's a deeper discussion. Right? So we're both all in on the Beam. Additionally, for the security point of view, I'm also all in on the secure L4 microkernel. And I know that this audience probably doesn't know a lot about it. It's one of the most shipped kernels in the world, and no one's ever heard of it. Imagine they took a kernel, they stripped it down to like 10,000 lines of code, and then built a formal proof, a mathematical proof of the kernel to know that it doesn't have certain security vulnerabilities. And then I'll just skip forward. And then these guys went deep on it. And this is, formally assured software is the direction these guys are going and how they think about kernels. Okay, back to this. So if it's good enough for those guys, then that sounds like something I'm interested in. But SEL4 is hard to use. In order to get it that small, they stripped out all the stuff that makes it easy. So I think I'm being fair here. It's really, really hard to program. So there's this vast middle ground of all these layers of what we're used to in an OS that need to get built on top. And if you have this opportunity, say, okay, I'm gonna use a really secure microkernel. I get to redefine how does the memory manager work? How am I gonna do scheduling? All these different things. But how would I design those knowing that the Beam is my first class citizen? So that's a space I've gotten to play in for a while. And by the way, in the way I think of this as like one of the world's hardest hello world projects. Oh my God. This has been, I fell off the cliff and I've gone into the deep end here. But I've been working on this for years now. And it feels like that Jello is finally not wobbling so much anymore. It's still shaking quite a bit, but it looks like a Jello. It's been molded. I think I can take the top off. It's going like this still, but it's actually getting there to the point where I can now talk about this and have some sense of confidence that it's going to actually look like this. So yeah, I hope to be talking to you guys in 2021 and showing off some interesting new operating system stuff working. I think we have time for a question or two. Is that how it's going to work?
Yes, indeed. Thank you. Very, very interesting presentations. Thank you so much. Indeed, we have some questions. Let me start with this one. I will read it out loud. This is about the language system should be simple, quote. Can you share a little about things that were removed to make it simpler?
Well, the communication mechanism is very simple between processes. You send a message to another process. It's purely asynchronous, and that's it, right? We had discussions on what to do about this. If you want more complex things, where do you put them? We had an idea of something we called a pipe, where you could send the message to the pipe, and the process at the other end would receive the message through the pipe and pluck it out of the pipe. And we had a pipe algebra for merging pipes and munging them and all things like this. It was a solution to a problem we thought that existed in the telecom app, and we built this. But then they came back and said, "Yeah, it's fantastic, but our basic premise was wrong. So all this was completely unnecessary." So we just removed that. Right? So we put a lot of work into do that. And how can we cut things down enough? How can we get the low levels right, so we could build everything we need on top of that, and not push the complexity down and have lots of complex ideas. I think that's, for example, why this communication is asynchronous. On top of the asynchronous communication with timeouts, you can basically build whatever level of security or safety you want in the communication. It took a bit of work to work that out, right? To show for ourselves that we could do that, but you can do that.
Something I'll back you up on with is, as I've been trying to work through inter-process communication down at the OS layer, I find myself mimicking some of the patterns that you've done. The asynchronous thing is really a great simplification.
Yeah.
It's not usable in every case, but Boyd is a big
Oh, no, I'm not saying it's usable every case, but sometimes you actually want synchronous communication, but you can build that on top of the asynchronous level. So I don't need to put synchronous communication at a low level. I can build whatever I want on top of that. And it's the same thing with the error handling mechanism. It's simple, but you can build whatever you want on top of that to get the right feel for it. That's where the simpleness comes in, and that's effort. Seriously, that's difficult, because chucking in new things all the time to solve a problem, that's easy, right? But then it gets really messy after a while. So I hope that answers the question for you.
Thank you.